Просто маленькие. Ow.
Tun, 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 tun. Психалик, мани, мани, хай. Давай говор. Купили как-то Гена в Чебурашках есть что?
Okay, hello, ladies and gentlemen. Can you hear me?
Yes, we can hear
Yes.
Yes, yes.
So let's begin. Last time we considered various questions concerning the GCD, that is the greatest common divisor of two numbers. We established some results about it, like Bezout's identity and some others. And now we want to explore the properties of exponentiation, that is taking powers. So what if I want to compute a to the power n modular m? In general, if I had no modular here, if I need the absolute value of this number, of course there is not much I can do in order to optimize the process. Of course, there is the algorithm of fast exponentiation. So one can do it better than multiplying a by a by a n minus 1 times. But nevertheless, the number grows rapidly, so it is not very good in general, and practically taking powers some modular m is way more nice. What is the main idea? The main idea is that these powers demonstrate some form of cyclic behavior. Let me quote the example well known to you, I hope, because we considered this problem during our seminar classes. Okay, what is the last number, or which is the same, the remainder modular 10 for the powers of 3? If I take 3 to the power 0, that is 1, I will obtain 1, of course. 3 to the power 1 is 3 modular 10. 3 to the power 2 is 9 modular 10, while 3 to the power 3 is 27 or 7 modular 10, and then 3 to the power 4 is 81 or 1 modular 10. So I have obtained 1 twice. After that, I will have a cycle, because, say, 3 to the power 5 is 3 to the power 4 multiplied by 3. That is just 1 multiplied by 3 modular 10. So I will have a cycle of this form: 1 3 9 7 1 3 9 7, and so on. Of course, if I have a cycle of length 4, I will have a cycle of length 8, of 8 length 12, and so on. Clearly, for 3 and 10, this cycle of length 4 is the shortest one. But we won't consider this question, which length is the least possible, but we will prove a theorem that guarantees that guarantees some length for this cycle. It will say that for some specific length, there is a cycle of that length. In order, we will have something like that. A to the power phi of n, where phi of n is some function of n, it will be congruent to n modular, or let it be m. It will be congruent to 1 modular m, so we will have a cycle of length at most phi of m. Is it clear?
Yes.
But what is this function phi of m? In order to define it, let's consider some numeric examples. Assume that m indeed equals 10. And now let's consider all numbers from 1 up to m minus 1. Here we have, of course, 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8, 9. Which of these numbers are co-prime to m? By the way, what does it mean that some numbers are co-prime to each other?
One number.
One number?
The greatest common divisor for them is 1.
Yeah. The greatest common divisor equals 1, or equivalently, the only possible natural common divisor is 1. Or equivalently, there is no prime common divisor for these numbers. So no prime divides both these numbers. Aha! So let's consider these 9 numbers. Which of them are co-prime with 10? One is obviously co-prime, of course, the greatest common divisor of 1, and anything non-zero equals 1. Indeed, the greatest common divisor of 1 and anything equals 1. So 1 is co-prime with 10. What about 9? 9 is also co-prime with 10 because the difference is 1. And if they had some common prime divisor, then 1, the difference, would be divisible by z prime, which is not possible. So m and m minus 1 are, of course, always co-prime when m is greater than 1. Okay, m is greater than 1, assume it. Which other numbers are co-prime with 10? Is 2 co-prime?
No.
No. Is 3 co-prime?
Yeah.
Yes.
4?
No.
In fact, no even number is co-prime to 10 because they have a common divisor 2. 5 is not co-prime either, so we have just 1, 3, 7, 9. Is it clear?
Yes.
So we have 4 such numbers, 4 co-primes to 10 among the numbers from 1 to 9. And what if I consider, say, 9? For 9, I have 1, 2, 3, 4, 5, 6, 7, 8. As above, 1 and 8 are co-prime to 9. It is quite clear. What else?
2.
2.
Every odd
4,
number.
5. No, of course not. We have 3 and 6 here, which are not co-prime because the common divisor, they share 3 as a common divisor with 9. So we have 6 such numbers. Interesting. And what if we take, say, 11? What if we take 11? 11 is prime, by the way. And this means that every number which is less than 11 is co-prime than 11, because the only possible prime divisor of 11 is 11 itself. And of course, no number less than 11 is divisible by it. Is it clear?
Yes.
And what about what about 12? What about 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of course, every prime as well as 1, all these numbers are co-prime to 11. And what about any other number? Is any even number co-prime to 12?
No, because
No, because 12 is even itself. Likewise, no number, no multiple of 3 is co-prime with 12. So these are the only possible numbers. So 4 such numbers. Is it clear?
Yep.
And now I will define some special function. It is called phi. It is denoted by phi, and it is known as Euler's totient. Please notice this strange word. Euler's totient function. Euler's totient function. And this function, by definition, returns the number of co-primes with M1, the numbers 1, 2, and so on up to M minus 1. We see that the behavior of this function is quite complicated. Say for 9, it returns 6. But for 10, it is just 4. For 11, it is 10. And for 12, it is 4 again. Is it clear?
Yes.
At some later stage, we will derive a general formula for this function, but for now, we don't need it. But we want to prove the following theorem by Euler. You know, Euler was a very prominent Russian mathematician of Swiss origin, who was a real classical author in mathematics, in number theory, in analysis, in mechanic, and many other areas. So this theorem by Euler states that if we have some number A, which is co-prime to our modulus M, will assume that M is greater than 1. If A is co-prime to M, then A to the power phi of M is congruent to 1 modulo M. So it is necessary that we have a cycle of length phi of M, of at most this length. Of course, this doesn't exclude that shorter cycles are possible. Is this idea clear?
So phi it shows the most long cycle. How many steps we have in them? Just the most long.
Yeah. By the way, we have a question. Not 11, of course, but 10 such numbers here. Thank you. A little correction. Thank you. So, I want to say that a to the power at most phi of m is necessary 1. It is possible to obtain 1 earlier, I mean for non-zero power, but it is not guaranteed. So, let's prove it. First of all, let's denote the value of our tangent function by s. So, s equals phi of m. That means that there are s numbers among the numbers from 1 to m minus 1, which are co-prime to m. So, let q1, q2, and so on, qs be all and only the numbers among 1, 2, and so on up to m minus 1, which are co-prime to m. Is it clear? So for every q, I have this equation. Is it clear?
Yes.
And now I will divide the proof into a number of very easy steps. The first step is as follows. If I and j are distinct, then qi is distinct from qj. And moreover, they are not congruent modulo m. Is it clear? Or should I prove it? Or is it obvious? Oh, probably I have to prove it. You know, qi is not equal to qj if I is not equal to j, because they are distinct. We have as distinct numbers, but every such number is, of course, less than m minus 1. And it is, so they are between 0 and m minus 1. Is it clear? In fact, they are between 1 and m minus 1. Is it clear?
Yes.
What is the, do you agree that the difference, the absolute value of the difference is greater than 0 and less than m?
Yes.
That means that the difference cannot be a multiple of m. Is it clear? So if the difference is not divisible, then they are not congruent. I think it is obvious, isn't it? So they are non-congruent. In fact, we know that no two numbers from this range are congruent modulo m, because if they are congruent, they have the same remainders. while these numbers coincide with the remainders modulo m. So if they are distinct, the remainders are distinct. Is it clear?
Yes.
My next step is as follows. If I differs from J, then not only Qi, but even A multiplied by Qi, AQi is not congruent to AQJ. Why is it so? It is easier modulo some previous knowledge. We know from the previous lecture that if AX is congruent to AY modulo M and A and M are co-prime, then I can cancel A out. So X is congruent to Y modulo M. So it is possible to cancel A out. Is this idea clear?
Yeah.
So if AQI were congruent to AQJ, then of course QI would be congruent to QJ, which is not the case. So they are not congruent. Aha! So they are pairwise not congruent. What's next? Let's define Ri to be the remainder which AQI leaves modulo M. Is it clear?
Sorry, why did you put not congruent QI to QJ?
Yeah. But nevertheless, my previous writing was formally correct, of course, because they are not congruent indeed. But if this were true, then they would be congruent, while they are not. Whence a contradiction? So AQI and AQJ are not congruent. Do you agree? I hope you do. So, what does Q mean? What is Q? Let Q1, Q2, Qs be all the numbers among the numbers from 1 to m minus 1, which are co-prime to m. These are all co-primes with m. This is all these numbers whose quantity phi counts. So, for example, for m being equal to, say, 12, Q1 maybe 1, Q2 maybe 5, Q3 is 7, and Q4 is 11. Is it clear?
Yes, thank you.
Okay. So, these Q's are all numbers between 1 and m minus 1, which are co-prime to m. Now we know that AQI and AQJ are pairwise non-congruent modulo m. Let's consider the remainders modulo m. I say that the remainders are distinct. Is it obvious? Okay. You know that two numbers are congruent some modulo m if and only if the remainders are the same. Is it clear?
Yes.
So these numbers are not congruent. Hence, the remainders are distinct. Is it clear?
Yes.
So on the one hand, these numbers are pairwise distinct. So R1, R2, and so on up to S, RS are pairwise distinct. On the other hand, all these numbers are, of course, between 0 and m minus 1. They are less than m by the definition of the remainder. Is it clear?
Yes, I think.
My next goal would be as follows. I want to show that these remainders are co-prime with m. Every remainder is still co-prime with m, as q's are, r's are also co-prime. Let's prove this fact. In order to do that, first I want to prove that AQI is co-prime to M. Let's prove it. You know that in order to prove that two numbers are co-prime, it is enough to prove that every common natural divisor is 1. Is it clear? Is it clear that it suffices to prove that the only natural common divisor is 1?
Yes.
So let D be some natural number which divides both AQI and M. Of course, I want now this D to be equal to 1. Let's prove it. In order to prove it, I will demonstrate some sub-goal for prime. I will prove that indeed this D is co-prime to A. It is co-prime to A. I will use the same method. I will assume that D prime is a natural number and D prime divides both D and A. Aha! You know, D divides M. D prime divides D. What can one derive therefrom?
D prime divides M.
Yeah. D prime divides both A and M. But we know that by our assumption, by the assumption, A and M are co-prime. Do you agree?
Yes.
A and M are co-prime. So as they are co-prime, as the greatest common divisor of A and M is 1, that means that D prime is what?
1.
It is necessarily 1. So every common natural divisor for D and A is just 1. So D and A are co-prime. But we know the following important fact. We know the following important fact. Assume that X divides Y multiplied by Z. And X and Y are co-prime. Then X divides Z. Do you remember this fact?
Yes.
So one can somehow cancel Y out. If Y is co-prime to X, then X must divide the remaining part of this product, that is Z. Aha! And now I know that D is co-prime to A. D is co-prime to A. Then I will use this fact and this one. D divides AQI, but is co-prime to A. Then D divides what?
QI.
D
Right.
must divide QI. But what do we know about these numbers QI? QI,
It's co-prime with
they are chosen to be co-prime with M. All these Q's are co-prime with M. As they are co-prime, so we know that the greatest common divisor of QI and M is 1. But D divides both QI and M. So then D must be 1. Is it clear?
Is it possible that D will be equal to Q1, QI?
To QI, then QI is 1. Of course, it is possible. But the only case is when D equals
Okay, thanks.
QI. QI can be 1. Why not? Is it clear?
Yes.
So
Yes.
at this point, I know that AQI is co-prime to M. My next step is as follows. I say that the greatest common divisor of Ri and M equals the greatest common divisor of AQI and M, which is 1 by the previous step. Is it clear? Why is it so? What is Ri? Ri by definition was the remainder. This remainder, but we know this was another theorem from our previous lecture. We know that given some x and some y, which is not 0, the greatest common divisor of x and y always equals the greatest common divisor of y and of the remainder. Do you remember this fact? We proved it last time. Please check. So, and we will exploit it later as well. The greatest common divisor of a divisible and a divisor is the greatest common divisor of the divisor and the remainder. Applying this fact, we will of course obtain this equation. Is it clear?
Yes.
So we have accomplished our task. We have proved this goal. This every number R is co-prime to M. Do you agree?
Yes.
Now, let's summarize our results. R1, R2, and so on up to Rs are distinct numbers from 0 to m minus 1. And I know that each of these numbers is co-prime to m. We know that m is greater than 1. Can 0 be co-prime to m? No. Is it clear? You know, 0 is divisible by m, but m is greater than 1. So 0 cannot be co-prime to m. Is it clear?
Yes.
Yes.
So what can we say then? Our R's, in a good sense of this word, These numbers are co-primes, are co-prime to M, and belong to this range. They all belong to this range from 1 to M minus 1. Do you agree?
Yes.
Yep.
Mhm. And what's the difference between R's in the innocent sense of this word and Q's? You know, Q's, we have S Q's, and all these Q's are all and only numbers. M1, 1, 2, and so on up to M minus 1, which are co-prime to M. And R's are just those numbers. They are co-prime to M. They belong to this range, and we have exactly S of them. Is it clear enough that R's and Q's are the same?
Yes.
So, the set of all Q's and the set of all R's, they do coincide, they are the same. Of course, it is not necessary that they are index-wise equal. So it may well be that Qi is not equal to Ry, but all these numbers taken collectively, taken together, they are the same as R's. Is it clear?
Yep.
So this is our main conclusion. The last step is easy and straightforward. Let's consider the product of all these R's. You know, every number is congruent to its remainder. So Ri is congruent to AQI modulo M. Is it clear?
Yes.
So this product is congruent to this one. Or regrouping, we have A to the power S and the product multiplied by the product of all Q's. But we know that Q's and R's are the same numbers. So the product of all Q's is just the product of all R's, maybe only orders, or only order is different, only the order differs. Is it clear?
Yes.
So what do I have? I have that the product of these remainders is congruent to A to the power S multiplied by the product of these remainders. But now let's recall the fact we have already mentioned. We know that it is possible to cancel some numbers out from a congruence. If x is congruent to ay modulo m, whereas a is co-prime to m, then x is congruent to y modulo m. Is it clear?
Yes.
But for every I know that this R is co-prime to M. So I can easily cancel out R1, R2, R3, and so on, up to RS. What should I obtain?
1
is congruent to a to the power s modulo m. But what is a to the power s? We have denoted the Euler's function value by s. S was just the value phi of m. Is it clear?
Yes.
So we have proved our theorem. Here it is. Quod erat demonstrandum. What was to be proved? QED. Is it clear?
Yep.
Do you have any questions?
No.
Mhm. As a corollary, we can obtain the following result, which is known as Fermat's. Fermat was another prominent mathematician from the 17th century, Fermat's little theorem. Fermat's little theorem says that if P is a prime number, if the number P is prime, and P does not divide A, then A to the power P minus 1 is congruent to 1 modulo P. How is it possible to prove it? That's easier. First of all, as P is prime, what is the value of the totient function? Which numbers from 1 to P minus 1 are co-prime to P?
All of them.
All of them, yeah. All these numbers are co-prime, so phi of the prime number P equals P minus 1. And we know that as P does not divide A, then I say that P and A are co-prime. Why is it so? It suffices to prove that A and P have no common prime divisor. Assume they have. But that means that their common divisor is P. The only prime divisor of P is P itself. Is it clear?
Yes.
But A is not divisible by P by assumption. So they must be co-prime. They can share no prime divisor, because the only possible such divisor is P, but A is not divisible by P. So by Euler's theorem, we have that A to the power P minus 1 is congruent to 1 modulo P. Is it clear?
Yes.
Another form of Fermat's little theorem is as follows. We can lift this assumption that P does not divide A. If P is prime, then A to the power P is congruent to A modulo P. Why is it so? It is obvious. Two cases. If P does not divide A, then A to the power P minus 1 is congruent to 1 modulo P. This is by Fermat's little theorem. And then you can multiply both sides by A, which will result in the required congruence. Is it clear? And if P divides A, then A to the power P is what? p is greater than 1 as it is prime. So a to the power p is divisible by p. And a is divisible by p. Is it clear? By the way, do you realize that x is divisible by m if and only if x is congruent to 0 modulo m? Is this statement obvious to you?
Yes.
Of course. So we have proved this form of Fermat's little theorem. And now let us see how is it possible to practically apply Euler's theorem or Fermat's little theorem for prime numbers in practical computations. First of all, I will derive another corollary which says the following. If A is co-prime to M and X and Y, some naturals X and Y are congruent modulo phi of M, then A to the power X is congruent to A to the power Y, this modulo M. Is this idea clear? So in order to get a congruence modulo M for the powers, it is enough to get a congruence for the exponentials modulo phi of M. Is this idea clear? Is it clear or not?
It is.
So let's prove this corollary. First of all, if x is congruent to y modulo phi of m, that means that the remainders are the same. So there exists such k, l, and r, so that x is phi of m k times plus r, while y is phi of m l times plus r. I have just divided x and y by phi of m with the remainder. So what is a to the power x? It is a to the power k multiplied by phi of m plus r, that is a to the power phi of m to the power k multiplied by a to the power r. Is it clear?
Yep.
And likewise for a to the power y. Here it is. Is it clear?
Yep.
And now let's consider a numerical example. Assume that I want to know the last digit in this number. One, many times, say 2021 times. I want to know the remainder modulo 10, the last digit. How is it possible to obtain it? Let's denote this number by n. So 1, 2, 4, 5, 6, 7 to the power n is congruent to which number to the power n? So first of all, do you agree that this number is congruent to 7 modulo 10?
Yes.
So it is congruent to 7 to the power n. So we know quite well what we can do with the base of our power. But what should we do with its exponential? we have to treat our exponential using this lemma. So we need to compute the remainder of n modulo phi of 10. But what is phi of 10? What is phi of 10? We have already computed it.
4.
Phi of 10 is just 4. Phi of 10 is just 4. As it is 4. So we need to know what n is congruent to modulo 4. But what is n? N is 1, 1, 1, 1 many times. So it is 100 multiplied by something plus 11. Do you agree? 100 is congruent to 0 modulo 4. And 11 is congruent to 3 modulo 4. So it is just 3. Is it clear?
Yes.
So by the previous corollary, 7 to the power n is congruent to 7 to the power 3 modulo 10, which is easy to compute because 49, 7 squared is minus 1 modulo 10, so it is minus 7 or just 3. So the last digit of this enormous number is just 3. Is this idea clear?
Sorry, can I have a question? Can you please explain one more time about n equals 3 mod 4?
N is of this form 1, 1, 1, 1. This part is divisible by 100. Isn't it? I mean this one. This is of the following form 100. So, okay. Do you agree?
Yes.
So it is just 100 multiplied by some k plus 11. 100 is congruent to 0 modulo 4. It is divisible by 4. Whence we have just 3, as 11 is congruent to 3, or isn't it?
Yes, thank you.
Why we get 4?
Why we get 4 here? Because phi of 10 is 4.
Oh, yeah, okay.
This is just by definition. Which numbers are congruent to 10 and less than 10? These are 1, 9.
Yeah, I got it. Yeah.
3 and 7. Any more questions? No. Okay. Our next topic will be the so-called Euclidean algorithm. What is the point of that Euclidean algorithm? We know that for every a and b, which are non-zero, there exist two numbers u and v, so that au plus bv equals the greatest common divisor of a and b. Do you remember it? It was a slight generalization of Bezout's identity. Do you remember this fact? But the problem is as follows: how to practically find the greatest common divisor of a and b and these numbers u and v. How is it possible to find these numbers? This question is important in the following respect. When we have to solve such an equation for integers, it will be necessary to find such U and V and the greatest common divisor of A and B. In order to solve such Diophantine, Diophantово уравнение, in order to solve such an equation in integers, we will see that it is sufficient to find both the greatest common divisor of A and B and such U and V. How is it possible to find them? Of course, when you know the factorizations of A and B, it is very easy to find the GCD. We have a formula. Do you remember it?
Yes, with maximums.
Yeah, with maximums of the exponentials.
Yeah,
In
yeah.
fact, with minima of the exponentials. But
Yeah, maximums.
in order to obtain this formula, in order to apply this formula, we have to factorize our numbers. And practically, it is a very hard problem for numbers big above. So, for big integers, it is very hard to factorize them. But fortunately, there is a better way to do so. Okay, let's start with an example. For short, this Euclidean algorithm boils down to the following rule. Divide the divisor. Divide the divisor. Which divisor? The divisor in an integer division procedure. So if you divide A by B, then B is called the divisor. Divide the divisor by the remainder. So this is the general recipe, which is known as the Euclidean algorithm. Let's try it. Assume that we have 26 and 34. I want to divide 26 by 34. So please, 26 equals 34 multiplied by something plus the remainder. Give me the partial quotient and the remainder.
0 and 26.
0 and 26. 26 is less than 34, so it counts as the remainder. And now I will apply our recipe. I want to divide the divisor, that is 34, by the remainder, that is 26. 34 is 26 by plus
8.
8.
1 and 8.
And 8. So the partial quotient is 1 and the remainder is 8. Okay. Let's apply it again and divide 26 by 8. 26 is thrice 8 plus 2. And now we have something interesting, something new. The divisor 8 is divisible by the remainder 2. So the last remainder is 0. As it is 0, it is not possible to continue. It's impossible to continue. Is it clear? Because it is not possible to divide by 0. So our algorithm has terminated. Is this idea clear?
Yes.
And now let us see what we will have in general. In general, we have some A and some B. B is not 0. So we start with dividing A by B. This will result in some partial quotient Q1 and some remainder, which I will denote R2. And now Of course, this remainder is less than the absolute value of b. This is by the definition of the remainder, and assume that it is still less, still greater than 0. So it is still possible to do one more step. Of course, it is possible that this remainder is 0, but it is not interesting. Assume that we can make one more step of our procedure, that is of dividing the divisor by the remainder. Now, the divisor was b and the remainder was r2. I want to divide b by r2. This will result in some partial quotient q2 and the new remainder r3. R3 is of course less than r2, and let's assume that it is not the final step. So we have a number greater than 0. Is this idea clear?
Yes.
Then we can divide r2 by r3, getting q3 and r4. Assume that r4 is still non-zero, but nevertheless it is strictly less than r3, and so on. Our general in the general form, our step will look like that. Rq is divided by rq plus 1, resulting in the partial quotient q k plus 1, and the next remainder r k plus 2. And of course, this remainder in principle, it can be 0, while this will be our last step. Is this idea clear?
Yes.
Yes.
So here,
It is less than RK, not RK plus 1.
yeah, rk plus 2 is less than rk plus 1. The remainder
Oh, right,
is
right,
less
right.
than
Okay.
the divisor. Okay. So now I want to prove that this algorithm indeed terminates. So it is not possible to do these operations indefinitely. Why is it so? It is quite clear. Do you agree that every remainder is natural?
Yes. Or 0.
0 is a natural number.
Ah, okay.
By the least number principle, LNP, by the least number principle, there is the least. There is the least. There is the least number rs plus 1 among r2, r3, r4, and so on. There is the least possible remainder. You know, this algorithm, every run of this algorithm generates some set of remainders. Do you agree?
Yes.
All these remainders are natural. In every non-empty set of natural numbers, we have the least one. So there is the least possible remainder. So this is the least possible remainder. I want to prove that rs plus 1 is 0. Assume it is not. If rs plus 1 is greater than 0, then we can divide one more time. We can divide one more time. So if it is not 0, that means that we can obtain we can divide rs by rs plus 1, which will result in rs plus 2, where rs plus 2 is less than rs plus 1. But is it possible?
Oh, by the least number principle.
No, of course. S plus 1 was the least remainder. It was the least remainder, so we have got a contradiction. Is it clear?
Yes.
Thus, the least remainder must be 0. The least remainder must be 0, but all the previous division steps were possible. That means that all the other remainders, all the previous remainders from R2 up to RS, they were greater than 0. Is it clear?
Yes.
And this, so we have got the following statement. We have proved it. We have proved the following proposition. The Euclidean algorithm, terminates. So it holds, it terminates. Is it clear? It doesn't hang, it terminates. And now let's pay some attention to this remainder, which was previous to the last one. Here we have that this remainder is exactly the greatest common divisor of 26 and 34. Is it clear?
Yeah.
No, 26 is just twice 13, while 34 is twice 17. Here we know the factorizations. We know that this GCD equals 2. But is it a coincidence? No, it is not. In fact, this Euclidean algorithm effectively provides us with the greatest common divisor. This last non-zero remainder, RS, will necessarily be equal to the GCD of our original number, statement 2. RS equals the greatest common divisor of A and B. Let's prove it. It is easy indeed. First of all, let's recall the fact we know. We have already used it today. So we used it today. And this fact is as follows. If A, let it be X and Y. For every X and every Y, which is not 0, we have that the greatest common divisor of X and Y is equal to the greatest common divisor of Y and the remainder. Do you remember this fact?
Yes.
So, with this in view, what the GCD of A and B equals to? It equals the greatest common divisor of B and R2 of the divisor and of the remainder. Is it clear? Is it clear?
Yes, the next step will be R3 and R2.
Yeah, of course. As our procedure was designed this way, divide the divisor by the remainder. That means that the greatest common divisor does not change. So this one equals the greatest common divisor of R2 and the remainder we have obtained here, which is R3. R3 is just the remainder after dividing B by R2. And then we will divide R2 by R3 with the remainder R4. So here we will obtain the greatest common divisor of R3 and R4, and so on and so forth. And in general, we will obtain here the GCD of RK
Okay.
and RK plus 1, which will equal the greatest common divisor of RK plus 1 and RK plus 2 and so on. And in particular, we'll obtain the greatest common divisor of RS and RS plus 1. Is it clear?
And the next.
RS plus 1 is 0.
Yeah.
It is not possible to divide further. It is not possible to divide further, but there is no need to do so because the greatest common divisor of a natural number and 0 equals this natural number. So here it is. The greatest common divisor of A and B equals the last non-zero remainder in the Euclidean algorithm. Is it clear?
Yes.
Yes.
So now we know how is it possible, how it is possible to compute the greatest common divisor without any factorizations, just by doing chained integer division, which boils down in its turn to chained subtraction. And how is it possible to find U and V? In order to obtain U and V, we need something more, but it is not hard to extend the Euclidean algorithm in such a way that we will obtain this U and V. And this procedure, let me finish this topic today. This is known as the extended Euclidean algorithm. The extended Euclidean algorithm. What does it mean that it is extended? In fact, in the Euclidean algorithm, we obtain two sequences of Qs and of Rs. Is it clear? In general, doing these sequential divisions, we obtain two sequences of numbers. Is it clear?
Yeah.
And this one is our general equation for which connects these two sequences. Let's rearrange it for RK plus 2. From this equation, we know that RK plus 2 is just RK minus RK plus 1 multiplied by QK plus 1. Is it clear?
Yes.
It is the same. And this is true for every natural Q. This is true for every K starting from 2. Because the first number of the remainder was 2. And now I want to somehow lengthen our sequence. I will add 2 more values for R. I will say that R0 equals A and R1 equals B. Then this statement will be true for every natural K. Is it clear? Because R2 equals just A minus B Q1. Q1 was the partial quotient resulting from dividing A by B. Is it clear? So
Yep.
R2 is just R0, that is A, minus R1, that is B, multiplied by Q1. So now, with this extension, our equation holds for every natural K. Is it clear?
Yes.
And now let's add two more sequences. Let's add two more sequences. One sequence will be for use, and the other one will be for with. I'll define U0 as 1, V0 as 0. U1 will be 0, V1 will be 1. And for all the other naturals, I will mimic this very equation, but I will change R's for U's and for V's respectively, so that I will put UK plus 2 to be equal to UK, United Kingdom, minus UK plus 1 multiplied by QK plus 1. And likewise, VK plus 2 will be equal to VK minus VK plus 1 multiplied by QK plus 1. Is it clear? Is it clear? I want to put it this way. I want to define these two sequences. May I?
Yes.
Why not?
But no, I will prove the following lemma. For every natural Q, RQ, for every natural K, RQ will be equal to A by UK plus B by VK. So I will prove that every remainder is expressible as a linear combination of A and B using just this U and V. Okay, let's check it. I will apply induction. Formally, this is an application of the strong induction principle, but I will go somewhat informal. Everything will be clear, I hope. So as the base, I will consider two cases. When so by induction on K, let's consider the base. As the base, I will consider two cases for K being equal to 0 and K being equal to 1. For 0, I have that R0 is A. Why? By definition. Do you agree?
Yes.
On the other hand, it is A multiplied by 1 plus B multiplied by 0. So it is A multiplied by U0 plus B multiplied by V0. That's quite clear. Likewise, for K being equal to 1, I have that R1, which is B, equals A multiplied by 0 plus B multiplied by 1. That is A U1 plus B V1. Is it clear?
Yes.
So these two cases are clear. And now, formally applying the strong induction, I can assume that for every number less than my given one, I have this equation. But in practice, only two previous numbers are needed. So I can put it the following way. I may assume that for K, my statement is true. And for K plus 1, it is true as well. So it is enough to prove that it holds for K plus 2. Is it clear?
Yes.
Why did you write k plus 2 for v?
Why
Yeah,
not?
no, it is
What's the problem?
in our induction hypothesis.
Here. Yeah, thank you. It must be 1.
Mhm.
So let's prove it. It's very easy and will require no more than 1 minute. R k plus 2 is by our universal equation for R's, which follows directly from the Euclidean algorithm definition. So this one is just Rk minus Rk plus 1 multiplied by Qk plus 1. Do you agree?
Yep.
And now let's apply our inductive hypothesis. So what is it? AUK plus BVK minus QK plus 1 multiplied by AUK plus 1 plus BVK plus 1. And now let's group together the terms for A and for B. So for A, we have what? We have UK minus UK plus 1 multiplied by QK plus 1. Likewise, we have here B multiplied by VK minus VK plus 1 multiplied by QK plus 1. Is it clear?
Yes.
And now let's look at the definition of our U sequence and V sequence. By the definition of these sequences, we have that this is exactly UK plus 2, and this one is exactly VK plus 2. Is it clear?
Yes.
So applying the induction principle, we see that for every k, Rk is equal to AUK plus BVK for some specially crafted sequences of U's and V's. And these sequences can be computed given the sequence of Q's. If we know Q's, which we determined from our Euclidean algorithm, if we know Q's, we know U's and V's. So for every k, we have that Rk equals AUK plus BVK. Is it clear?
Yes.
And in particular, we can take k being equal to S, but Rs is the greatest common divisor. So as a corollary, one obtains that the greatest common divisor of A and B, which is just Rs, equals A US, United States, plus BBS. So in order to get these numbers, such numbers U and V, so that AU plus BV equals the greatest common divisor, it is enough to compute U number S and V number S in this sequence. So we have successfully completed this task of finding U and V such that the respective linear combination of A and B equals the greatest common divisor. Is it clear?
Yes.
Next time, we will apply all these procedures to solving an equation of the form AX plus BY equals C, where A, B, and C are integers, and it is necessary to find a pair of integers X and Y which make this equation true. Any questions, please? So please memorize this Euclidean algorithm, and it would be very beneficial for you if you try to apply the extended Euclidean algorithm to some particular number. And a very good starting point is to extend this application of Euclidean algorithm. So try to compute u and v so that 26u plus 34v equals 2. Try to compute them using our general procedure. Any questions? Then I thank you. Do you need the whiteboard copy?
Yes,
Yes,
please.
please.
Please take it. I've sent it. So have you received it?
Yes, thank you.
Thank you, dear students. Thank you. Please do not forget about our course, even though we have this unholy holidays. You always have a choice. Either you study or you're getting lazy and do nothing. Okay, so thank you. Goodbye.
Thank you. Goodbye.
Bye.
Thank
Goodbye.
you.
Bye.
Thank you.
Goodbye,
Bye.
ladies and gentlemen. Goodbye.
Thank you. Bye.
Thank you.